When we look up at the night sky, we see countless stars. But what we can't see is at least as fascinating: planets orbiting these distant suns. These worlds outside our solar system are called exoplanets, or extrasolar planets. An exoplanet is defined as a planet that orbits a star other than our Sun. This definition may seem simple at first, but it opens up a universe full of possibilities. Each of these planets is a world unto itself, with its own properties, temperatures, and potentially even life forms. The study of exoplanets is therefore of fundamental importance for our understanding of the cosmos and our own existence. Furthermore, it allows us to assess the uniqueness or ordinariness of our own Earth. Is our blue planet a cosmic stroke of luck? Or are there millions of similar worlds out there? For centuries, exoplanets remained purely theoretical. The technical challenges were immense. Planets don't emit their own light. They only reflect the light of their stars. Discovering a planet orbiting its dazzlingly bright star is like trying to spot a firefly next to a lighthouse from 1,000 kilometers away. Discovering exoplanets requires sophisticated, indirect methods, because most of these worlds are too faint to be observed directly. Over the years, we have developed several clever techniques to track down these hidden planets. The most successful and productive method is the transit method. The principle behind it is elegant in its simplicity. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the starlight. Sensitive telescopes can detect this minimal dimming. Imagine observing a distant street lamp, and occasionally a moth flies in front of it. For a fraction of a second, the light dims ever so slightly. The transit method works on precisely this principle. The difference is that the dimming of exoplanets is often less than 1% and lasts for hours. The search for habitable worlds begins with the habitable zone, the region around a star where liquid water could exist on a planet's surface. Not too hot, not too cold, but just right. For our Sun, this zone lies between Venus and Mars, with Earth comfortably in the middle. However, the location of this zone varies greatly depending on the type of star. For cool red dwarf stars, planets must be extremely close to their star to remain warm enough. This proximity often leads to tidal locking. One side of the planet melts in perpetual heat, while the other freezes in darkness. Finding a planet in the habitable zone, however, is only the first step. The right size is crucial. Planets that are too small lose their atmosphere, while those that are too large become gas giants without a solid surface. The ideal mass lies between Mars and about twice that of Earth. Furthermore, a habitable planet likely needs active plate tectonics for a stable carbon cycle. An atmosphere regulates temperature and protects against radiation. The balance has to be right. Too many greenhouse gases lead to the Venus scenario, with temperatures exceeding 450 degrees Celsius. Too few cause the planet to freeze. With current telescopes, we cannot yet analyze the atmospheres of Earth-like exoplanets in detail. Liquid water is considered another fundamental requirement for life. The challenge here is that we cannot directly detect water on exoplanets. Even planets in the habitable zone could be bone dry. Water could also exist beneath icy crusts, as is presumed on Europa and Enceladus, but would then be invisible during planet searches. Despite the stringent criteria for habitability, we have discovered several exoplanets that appear promising at first glance. These worlds lie within their stars' habitable zones and are Earth-like in size. However, closer examination reveals significant uncertainties and potential problems that explain why none of these candidates are considered definitively habitable. Proxima Centauri b, discovered in 2016, is the closest exoplanet to us, only 4.2 light-years away. It orbits Proxima Centauri, a red dwarf star, within the habitable zone. With about 1.3 Earth masses, it could have a rocky surface. However, its proximity to its star presents massive problems. Its orbital period is only 11 days, and it is likely tidal. Even more critical are the star's powerful radiation bursts, which are up to 100 times more intense than solar flares. Such bursts could have long since stripped away any atmosphere and sterilized the surface. Without a protective magnetic field and atmosphere, Proxima Centauri b, despite its habitable location, would be a dead, radioactive wasteland. The TRAPPIST-1 system, 40 light-years away, attracted worldwide attention in 2017. 7 Earth-sized planets orbit an ultra-cool dwarf star, 3 of them in the habitable zone. The planet's dense arrangement allows for detailed mass measurements and makes the system an ideal laboratory for exoplanet research. But here too, there are serious concerns. TRAPPIST-1 is even more active and radiatively intense than Proxima Centauri. The planets are so close together that, viewed from one to the other, the neighbouring planet would appear larger in the sky than our Moon. This proximity leads to complex gravitational interactions. Initial observations with the James Webb Space Telescope indicate that at least some of the planets lack dense atmospheres. Kepler 442b, about 1,200 light-years away, was long considered one of the most Earth-like planets. It lies in the middle of the habitable zone of a K-type dwarf star, which is quieter than a red dwarf, but has a longer lifespan than our Sun. With a radius about 1.3 times that of Earth, it could be rocky. The problem is its great distance. We know practically nothing about its actual properties. Does it have an atmosphere? Is there water? Is it rocky at all? Or perhaps a mini Neptune with a thick gas envelope? The transit method only tells us its size and orbit, but nothing about its surface conditions. Kepler 442b thus remains a statistical hope without concrete confirmation. Why are these and similar planets not considered habitable, even though they seemingly meet the basic requirements? The crucial point is the difference between potentially habitable and actually habitable. A planet in the habitable zone is merely a candidate where temperatures could theoretically allow for liquid water. This classification is based solely on distance from the star and stellar luminosity. It takes neither the actual atmosphere nor surface conditions or the presence of water into account. The reality is more complicated. Venus technically lies at the inner edge of our Sun's habitable zone, but with a surface temperature of 450 degrees Celsius and a runaway greenhouse effect, it's hell on Earth. Mars lies at the outer edge of the same zone, but is a frozen desert with a paper-thin atmosphere. The habitable zone, therefore, is not a guarantee, but merely a first filter. With exoplanets, in most cases we don't even know the most basic properties precisely. We can often only roughly estimate their mass, cannot analyse their atmospheres, and can only speculate about their surface composition. A planet could have a dense, toxic atmosphere like Venus, be completely dry like Mars, or conceal a rocky surface beneath a global ocean. Without detailed measurements, we cannot distinguish between these scenarios. Added to this is the challenge of confirmation. Even if we were to find a planet with perfect conditions, the right size, at the right distance, with signs of an atmosphere, that would not yet prove habitability. Life itself, should it exist, would be even harder to detect. We would need to find biosignatures in the atmosphere, that is, chemical imbalances that indicate biological activity, like the high oxygen content of Earth's atmosphere. However, these measurements require technologies that we are only now developing. For Earth-sized planets, though, the signal is extremely weak. The atmosphere of an Earth-like planet absorbs only a tiny fraction of the starlight during a transit. Even the powerful James Webb Space Telescope reaches its limits here, requiring dozens of observations to gather usable data. A crucial conceptual distinction exists between potentially habitable and inhabited. A planet in the habitable zone of the right size may meet the conditions for life, but that doesn't mean life actually exists there. Earth itself was habitable for the first 2 billion years of its existence, but populated only by the simplest microbes. Complex life developed much later. A habitable planet could be completely sterile, while life could theoretically exist even in places we would consider uninhabitable. There's also a philosophical problem. We're looking for life as we know it, based on carbon, dependent on water, on solid surfaces. But life could take entirely different forms that we wouldn't recognize. Our criteria for habitability are inevitably shaped by our only example, Earth. Distance plays another critical role. Most interesting candidates are hundreds or thousands of light years away. Even the nearest exoplanet, Proxima Centauri b, is over 4 light years away. We can only analyze the faint light that reaches us and are forced to rely on indirect inferences. These challenges add up to a frustrating situation. Statistically, there should be billions of habitable planets in our galaxy. But actually identifying and confirming these planets is currently beyond our capabilities. Until then, even the most promising candidates remain just that, unconfirmed possibilities in a sea of uncertainty. I hope you enjoyed the video, and I'll see you next time.